So, just a bird's eye view of Raman spectra and how it all started. So, you all know about Sri Chandrasekhara Venkat Raman. The Raman effect is named after him. He won the Nobel Prize in 1930 for physics, and he discovered the Raman effect. And he also studied X-ray diffractions and various other fields like optics, dielectrics, ultrasonics, photoelectricity, and colloidal particles. So basically, Raman spectroscopy is a two photon scattering process, and these processes have to be inelastic. Just be familiar with this term, so we'll go into detail about these. So these two processes are inelastic scattering. One is the Stokes scattering, where the energy is lost by photon, and there is the anti-Stokes scattering, where the energy is gained by the photon. Okay, so photon in and photon out. But usually the dominant process is elastic scattering. That is known as Rayleigh scattering. Okay, that is known as the Rayleigh scattering. And if we have the incident photon energy as E and the vibration energy as V or nu, then in terms of energy, the photon that is coming out will have energy either E, that is Rayleigh scattering, which means the energy of the photon, incident photon, will be equal to energy of the outgoing proton, and there will be no loss or gain. Or it could have loss in energy, it could have less energy than the incident photon, which will be Stokes scattering, or it will have more energy than the incident photon, which will be the anti-Stokes scattering. Okay, so this is the basic principle by which the Raman effect starts. Okay, this is the basic principle through which the Raman effect starts. So we are going to go into more detail now as to what the basic definitions are. So essentially, as we discussed, when we are having a monochromatic radiation passing through a transparent medium, so we know what kind of effects it can have. Some of it is transmitted, some of it is absorbed, a small amount is scattered, and most of this scattered is at the same frequency as the incident radiation. Now, this is called elastic scattering or Rayleigh scattering. But sometimes it is scattered at a frequency that is higher or lower than that of the incident radiation. Now, because of this inelastic scattering, these scatterings are known as the Raman scattering. Now, Raman and IR, they form a very unique spectrum. So each molecular crystal has its own specific and unique Raman and IR spectrum. Now, molecules we know as continuously vibrating. So both the Raman and IR spectra, they detect and analyze the energy of the different vibrations that take place in the molecule, and these produce the spectrum. And that is why the radiation that is employed in Raman and IR, they are quite different. Because in IR, what we are doing, we are giving a entire range of radiation which covers the entire IR region, and that is directed onto the sample, and absorption takes place when the frequency of the radiation matches that of the vibration. So matching is a criteria for IR spectra. But here, Raman spectra just uses a single frequency source, because here what is the focus? This focus is that the scattered light from the molecule, whether it is elastic, inelastic, and how much it is scattered. Okay, so the quantum mechanical description is like this. Suppose you have a photon of energy h nu 0 colliding with a molecule, and it can be scattered elastically, okay, or inelastically. So you can see the diagram here. So here it shows the vibration and electronic energy level diagram of a molecule, showing the processes of IR absorption, Raman, and Rayleigh scattering, as well as fluorescence emission. So I suggest that you take this diagram just roughly in your copy. I'm giving you 1 minute. Just do the diagram in rough. Quickly do the diagram in rough, giving you 1-2 minutes to do it. You don't have to be neat, just quickly do it. Okay, so here we are saying that absorption is there from the vibrational levels of the ground state to the vibrational levels of the excited state, and the entire absorption is from the from the zero level to the uppermost level. And in fluorescence, we already know that the emission is taking place from the lowermost excited state to different vibrational levels. In Rayleigh, you see that if it is getting excited to some kind of a energy state, then it is coming back to that very level. But in Raman Stokes and Raman anti-Stokes, so what is happening? The incident photon is there and it goes to a particular energy state, but from the lower level from which it originated, the emission that is coming out, the photon that is coming out, is not going back to the original energy state. In both Stokes and anti-Stokes, like Rayleigh scattering, they do not go back to the original energy state. In Raman Stokes, it goes to the next upper level of ground state. It does not go to the original ground state, it goes to the next upper level. So the energy is decreased. And in Raman anti-Stokes, suppose that the absorption was from a slightly higher level, but in anti-Stokes it will go down to the level that is lower than the level from which it originated, giving rise to a higher energy photon. Okay. And in IR, just it is restricted to the vibrational levels and is not going to any other energy state. So this is the difference between IR, Raman, Rayleigh and fluorescence. Okay. Giving you another minute to just look at the diagram and copy it if necessary. I'll be sharing the PDF, but you should also draw diagrams when we are looking at it. Okay. So here the same thing has been told, that the collision with the photons induces the molecule to undergo a transition between two vibrational energy levels of the molecule, and the resultant scattered radiation has a different frequency than the incident photon. If during the collision molecule gains some energy, photon will be scattered at the frequency h nu 0 minus h nu vibration, and this is known as Stokes Raman scattering. If the molecule is losing some energy by relaxing to the ground state, then the scattered energy will be at h nu 0 plus h nu vibration. This is anti-Stokes Raman scattering, and they are usually represented in wave number shift relative to the excitation line. So there will be an excitation line, and from that relative, the shift in wave number is the measurement value. So here you can see an example of cerussite or lead carbonate. Okay, so this is the spectra where we can see the Stokes and the anti-Stokes line here. So here it is, we are saying that both the Stokes and the anti-Stokes band intensities, they can be measured in order to see the temperature in situ at the microscopic level at some specific positions of the sample. And at room temperature, the probability to have molecules in an excited vibrational state is low. So in the room temperature, you don't have many molecules in excited vibrational state. So the anti-Stokes scattering, it might be weaker compared to the Stokes intensity. Okay, it might be weaker compared to the Stokes intensity. Now, before we go to instrumentation, I also want to tell you something about the quantum mechanical model of Raman effect. So let me go to that. Just one second. Okay. So now for Raman spectra, there might be a pure rotational Raman spectra or mixed Raman spectra. So we have to first look into the selection rules of rotational spectra. It is not in there in your course, so I have not covered that much. But for microwave spectra, just go through the principles briefly. If you want some material from my side, I will also be sending it today. So I can send the material for microwave spectra. It is not there in your syllabus, but you can go through it because it has relevance for the understanding of Raman spectra. Okay. So just I will tell it to you briefly. Like we have selection rules for IR, we also have selection rules for how molecules rotate. Okay, they have an axis. So read up on the concepts of moment of inertia before you go into rotational spectra. So for a complete treatment, we need to see the quantum mechanical perturbation theory. So rotational selection rule is this. Okay, for microwave spectroscopy, usually the selection rule here is the delta J is equal to plus or minus 1. Okay, that is like you had seen in IR, that was also plus or minus 1. Delta nu is equal to plus or minus 1. For microwave spectroscopy, the quantum number that is being changed is delta J, and that is equal to plus or minus 1 for microwave or rotational spectroscopy. But when it comes to Raman theory, that the change in the rotational quantum number will always be 2. Okay, it will always be 2. So delta J is equal to plus or minus 2. Okay, delta J is equal to plus or minus 2. And also we you can read it from other sources. Expression for rotational energy level for linear molecules is Ej is equal to H into Bj into J plus 1, where J is equal to 0, 1, 2. Please note this down. Ej is equal to Hbj into J plus 1, where J is equal to 0, 1, 2. Okay, now we can write the delta Ej. Suppose we are writing J. Okay, suppose J is a particular level and J plus 2 is another level. Now the allowed transitions will be only between J and J plus 2 according to the selection rule. Delta J is equal to plus or minus 2. Okay, so let us just ignore the minus 2. Delta J is equal to minus 2. Let us see for only delta J is equal to plus 2. So if you're taking any level J, then the next level that can define the transition is J is equal to 2. So if you are applying this formula 3.6, okay, if you are applying this formula 3.6 and substituting J in the first expression and J plus 2 in the second expression, if you solve it, you will get HB into 4J plus 6. Please work it out. Giving you 2 minutes. It's not hard at all. Just look at the example here. Delta Ej is equal to Ej into Ej for J plus 2 minus Ej for J is equal to J. So just work it out whether you're getting BH is equal to, delta Ej is equal to HB into 4J plus 6. Whether you're getting this expression or not, please work it out. After you're done working it out, please give me a yes in the chat box once you're done, whether you got the answer or not. Have you got the answer? So in 3.6, you just have to substitute J plus 2 in place of J in the first term, and you have to just subtract this particular term from the first term. Just try once and then we will proceed. Type a yes if you are done. Okay, you will work it out yourself then. So J is the rotational quantum in the lower state, and here delta J is equal to plus 2. So first we have to refer to the lines arising from the energy changes as S branch. Okay, as S branch. So suppose S branch, we are taking us the Stokes line. Okay, it will be a Stokes line, and always you will get the S branch on the low wave number side of the exciting line. So the wave number of Stokes line are given as this much. Okay, where V nu x exciting is the wave number of the exciting line. Okay, nu bar x is the wave number of the exciting line, and nu s will be the wave number of the Stokes. So Stokes we have already defined as this much. So nu x will be equal to nu excitation minus B 4j plus 6 centimeter inverse. And similarly, the anti-Stokes line will be excitation wave number plus that of the spacing between the line, the wave number of the anti-Stokes. Okay. So here this diagram is very important. Okay, this diagram is very important. So usually when we are explaining Raman spectra, we give this diagram. Okay, so the middle value is the exciting line. Okay, middle value is the exciting line, and you will see that Stokes and anti-Stokes are lines that are given by vibrations, different vibrations, and they are spaced equally. They are spaced equally. So the first Stokes line and the first anti-Stokes line, they will be at a distance of 6b each from the exciting line. Okay, and subsequently for J is equal to plus or minus 2, the difference will be 4. Okay, the difference will be 4b. And for Stokes value, you already know how the absorptions are taking place. Okay, Stokes and anti-Stokes. So this particular, the lower particular diagram is explanatory of a Raman spectra and what is Stokes and what is anti-Stokes and where do they occur on the spectra. Here also you note this equation down 3.10. The relative intensities, they depend on the relative population of the rotational levels. Nj by N0 is equal to 2j plus 1 e to the power minus e by kt. E to the power minus capital E, you do that. It's given in a confusing manner. E to the power minus capital E by kt. Theoretically, Stokes and anti-Stokes line should be comparable in intensity. Okay, they should be comparable in intensity theoretically, because there are so many different rotational levels and the downward transitions are as likely as the upward ones. So they are theoretically comparable in intensity unless other factors are affecting it. Okay, so you read this particular line. It can be seen that the frequency separation of the first Stokes or anti-Stokes line, which corresponds to J is equal to 0 from the exciting line, is 6b centimeter inverse. Here is what we have seen. So for J is equal to 0, for both Stokes and anti-Stokes line, the separation is 6b, which is what we have discussed earlier. The separation between successive lines on either side of the exciting line is 4b centimeter inverse. The separation between successive lines on either side of the exciting line is 4b centimeter inverse. So the first separation is 6b and thereby the separation becomes 4b. Now, which molecules give neither IR nor microwave but rotational Raman spectra? Okay, homonuclear diatomic molecules O2 and H2. Now, because they're connected by a single bond and they are symmetrical, so IR or microwave spectra they won't give any kind of spectra because there will be no change in dipole moment. Okay, there will be no change in dipole moment in homonuclear diatomic molecules, but they can give a rotational Raman spectra. Okay, they can give a rotational Raman spectra because very important point, Raman spectra depends on the molecular polarizability rather than on the molecular dipole. Okay, Raman spectra depends on the molecular polarizability rather than on the molecular dipole. So, but some kind of variation or diversity will be seen in these kind of linear molecules like oxygen or CO2 because there is a center of symmetry which is completely unoccupied. Okay, so here in the Raman spectra, it will show the spectra, but there will be some absence of alternate spectral lines. Okay, there will be some kind of spectral lines missing. So, in case of oxygen, anything with an even value of J will be empty. Okay, so any transition which is like J is equal to 0 to B, they will be missing from the spectrum of oxygen. And so instead of the spacing of the lines being 4B, the spacing of the line will be 8B. Okay, they will be 8B. Now for rotational energy transitions, let us look into some more lines. Here delta J, if it is equal to plus 1, it is known as the R branch and the difference in energy is 2HB into J plus 1. And if you have S branch lines, that is delta J is equal to plus 2, then the spacing is HB into 4J plus 6. Write this down. Okay, so now this particular one will be the expression plus or minus. We have already seen in Stokes it is minus, in anti-Stokes it will be plus. So final expression for two series of lines of frequency will be there. Nu s is equal to excitation frequency plus or minus b into 4j plus 1 centimeter inverse, where j is equal to 0, 1, 2. So there will be two lines. So the lines in the R branch will be at 4b, 6b, 8b, and 10b from the exciting line. The S branch lines will occur at 6b, 10b, and 14b. Okay. Now, what kind of molecules are affected by polarizability and which are Raman active and inactive? So, in case of spherical top molecules, spherical top includes CH4, SiH4, there is no change in polarizability. There is no change in polarizability. So, the pure rotation of spherical top molecules are Raman inactive. Okay, they are Raman inactive. But if it is an asymmetric top molecule, for example, chloroform, then they are normally Raman active and their Raman spectra is also extensively obtained. Okay, if there is a spherical top molecule, bond lengths are not changing and the difference in polarity is not much, the polarizability will not alter in case of rotation. But if there is a difference in polarity within the molecule, then they can be Raman active, okay, and their Raman spectra can be obtained. Now, this was about rotational Raman spectra. We also have a vibrational Raman spectra. Okay, we also have a vibrational Raman spectra where for the vibration mode, usually we write this kind of equation. Nu E is equal to n plus half. It is written as V here, but I'm taking as n plus half to prevent confusion. Nu E is equal to n plus half minus nu e xe into n plus half whole square. And the nu e bar is for the wave number thing. Okay, it is for the wave number, it is nothing else. And xe is the anharmonicity constant. And the selection rule is delta n. Okay, here I'm telling n. Delta n is equal to 0, plus or minus 1, and plus or minus 2. And this remains same for Raman as well as IR. Okay, this remains same for Raman as well as IR. And so, if you are having one particular fundamental frequency where the transition is n is equal to 0 to n is equal to 1 transition, then the fundamental vibration is this much. Now, this here I'm also covering a little bit of vibrational frequencies. In IR, we just learned the just the normal techniques and applications, but this is actually the quantum mechanical method. Might not be there in your syllabus, but I'm just going through it so that you can understand. So delta E fundamental will be h nu E 1 minus 2 xe. So this is because of the anharmonicity constant that xe is there. And fundamental can be there. Okay, the fundamental frequency will be there like this. If energy is that, then the fundamental frequency will be this. So here the plus sign, because we are dealing with exciting line, new excitation is there here. So excitation के बाद अगर plus sign हुआ, then it is the anti-Stokes line, and if it is a minus sign, it refers to the Stokes line. Okay, where nu ex is the frequency of the excitation radiation. Okay, it is the excitation radiation. So not much we can see from the vibrational Raman spectra. Usually it can show in the low frequency side there will be more intense lines. On the high frequency side there will be weakened mirror images. Okay, so it is basically for which molecule is Raman active and which molecule is Raman inactive. For that to find out the vibration is there. And finally, there is a combined formula. Okay, there's a combined formula for vibrational rotational Raman spectra. Okay, here it is nothing. It is just combining the formulas for what we have seen for rotational Raman spectra and vibrational Raman spectra. So this part is for the vibrational Raman spectra. We have already known nu E is equal to n plus half minus nu E x E is equal into n plus half whole square plus Bj into j plus 1. Okay, Bj into j plus 1. Finally, we are getting this one. Excitation line plus b into 4j plus 6 or minus b into 4j plus 6. So this is what we are getting. New excitation minus nu 0 minus b into 4j plus 6, or new excitation minus nu 0 plus b into 4j plus 6. Okay, so here we can get rotation vibrational spectra where this is your new excitation. Okay, new excitation is there, and nu 0 and nu s will be the new lines. Okay, nu 0 and nu s will be the new lines. Now in details I'm not going here because usually in exams this is not coming, but this is just for your extra reading. So you can refer to this PDF also. I'll be sending this one. So find out about vibration rotation spectra. It is usually quite complicated, and you will not be asked to draw the spectra or analyze the spectra in any manner. Just the basics you should know, and the quantum mechanical things you can apply it later when you actually do the spectroscopy. For a fundamental microscopic view, I just gave the explanation. Otherwise, this is not much required. So we will go back to our instrumentation now. Okay, we will go back to our instrumentation now and see what kind of instruments are being used. So let me just share screen for that. Okay, so like any other spectrophotometer, Raman spectra also is made up of 4 kind of parts. You will have a source. Okay, we will have a system that can illuminate the sample and collect the Raman signal, and finally a dispersive system, and of course a detector is also there. Now collecting system is very important here, and here because we are seeing the energies of the photon that are being scattered back and we are seeing what kind of spectra they are giving, we need a back scattering geometry kind of a collecting system. So here what is happening, that the laser light is focused with the collection lens onto the sample, and then the scattered Raman spectra, the scattered Raman lines, they're collected by the same kind of lens system, and then they are sent to the entrance slit of the spectrometer. Okay, you can do this one, or you can also collect the scattered light at an angle of 90 degree. So we need, whenever there is a Raman microscope, it should have a special backscattering illumination collecting system. So a typical microscope is usually to both visualize and focalize the laser onto a microscopic region of the sample and to collect the Raman signal. And as regards the dispersive system, usually we have seen monochromators are there, prisms and gratings are there. Here it discriminates the weak Raman scattering from the intense laser line, incident laser line. And how it discriminates? Because it is formed of several holographic gratings. Okay, holographic gratings. And CCD is now the typical detector that is used for Raman spectrometers. Okay, CCD is used as the typical Raman spectra. For detection of Raman spectra, CCD detector is used. So what is a CCD detector? Is a charged coupled device. Okay, it is a charged coupled device, and it is a highly sensitive photon detector. Okay, it is a highly sensitive photon detector. Essentially, it is kind of an integrated circuit which contains an array of linked or coupled capacitors. Okay, it can have a linked or coupled capacitors, and it is also divided up into a large number of light sensitive small areas known as pixels. Okay, and CCD sensors are now a major technology which is used in digital imaging also. Okay, it is also used in digital imaging. So the same kind of detector is also used for Raman spectrometers, and we require that for elimination of noise. These detectors, they are often cooled at liquid nitrogen temperature, and so even weak signals can be picked up. Okay, even weak signals can be picked up. Also, some instruments use filters technology with one shot focal length grating instead of holographic gratings. They will use only one kind of grating and they will combine it with optical fibers. Okay, they will combine with optical fibers. Also, like in FTIR, we have the Fourier transform. FT Raman system is also there, and it uses a Michelson interferometer. So even in some systems, for complete vibrational description, the FT Raman and the FTIR instruments are also coupled. Okay, so you can get a complete vibrational description of materials. Okay, so with the evolution of Raman microscopy, now we can even study very small samples. Okay, and we can also resolve the samples in both lateral and axial formats. Now let's look into the advantages and limitations of Raman spectroscopy. So as we have said, the resolution is very high and very little sample is required. So this is the prime advantage, that very high resolution can be achieved with very little amount of sample. Okay. Also, you do not need to prepare a very specialized kind of a sample. Even if you have a small size or any kind of type of sample, they can be easily analyzed as they are received. So you do not have to do a special sample preparation. Like in IR, we had to do a little bit of mulling. You add a little bit of solvent, you knead it, you put it in, you do it in form of a tablet, then you analyze the sample. Here no sample preparation is required. So all types and sizes of sample, they can be easily analyzed as received. Next, glass does not interfere with Raman spectrum. Okay, glass does not interfere with Raman spectrum. So traditional optics, they are suitable for Raman spectroscopy. Okay, so traditional optics are suitable for Raman spectroscopy. And simple accessories can be easily adapted for Raman measurements, like temperature and pressure cells, optical fibers for remote analysis, reactors for in situ experiments. So these can be easily adapted for Raman measurements. In fact, since glass does not interfere, any kind of a glass, kind of a tube or a vial, they can be used for solid, powder, liquid, and gases. As mentioned before, we do not need any kind of sample preparation. Okay. Even if you're using any kind of a tube, like even that if it is measured of a made up of a quartz or plastic, and if it is in a sealed format, that also can be used. And as I told you, many kinds of samples can be analyzed. If your sample is dissolved in an aqueous solution, then you can again use that for vibration Raman spectra, because the Raman spectrum of water is quite weak. So you can easily detect that peak and you can just strike it off. It won't make any difference, or it won't complicate your spectra. Okay, it won't give you the extra peaks that will complicate your spectra because it is a very weak signal. So even if your sample is there in aqueous solution, you can go ahead and record the Raman spectra. Also, the whole vibrational spectra from 5 centimeter to 4500 centimeter inverse, it is readily obtained, and at very low frequencies and internal modes you can get the information for both vibrational and Raman spectra. Also, the Raman bands are quite well resolved, we have already told that, but the baseline is also flat. Okay, baseline is also flat provided no fluorescence is occurring. So structural characterization becomes easy. Also, now the Raman systems, they are offering the possibility to record both Raman and photoluminescent measurements in the UV, visible, and near IR regions. Okay, in the UV, visible, and near IR regions, they can offer the possibility to record both Raman and photoluminescent measurements. Next, the Raman intensity is proportional to concentration, so quantitative analysis is quite simple. Raman intensity is proportional to concentration, so quantitative analysis is simple. Because we can couple optical fibers to Raman spectrometers, now these kind of spectrophotometers are also used in industrial plants where you can control and monitor, and the quality control lab can be separated from the process line. It can be located at some other place also. So what are the drawbacks of Raman spectra? We have already discussed it, but you did not realize it, that it is very weak. Okay, it is very weak. So if you have, first thing, very low concentration mixtures, very dilute solutions, you cannot use that because it will give a weak signal, extremely weak signal. Also, if you have any kind of material that will fluoresce, or any samples that have fluorescent impurities, it will strongly interfere with Raman signal. So Raman ka ek hi dushman hai, and that is your fluorescence. Anything that will have fluorescence will interfere with the Raman signal, and kyunki Raman signal weak hai, it will not show the proper result. So अभी we have several laser sources जहां पे कोई भी फ्लोरेसेंस अगर इम्प्योरिटी हुई भी उसका सिग्नल नहीं दिखाएगा. ओके, उसका सिग्नल नहीं दिखाएगा. So the new Raman systems with several laser sources, they avoid the fluorescence. Also, several technological developments have occurred which can increase the efficiency and the strength of the Raman signal, which is also known as Raman resonance or surface enhanced Raman spectroscopy, which is also known as SERS. Okay, surface enhanced Raman spectroscopy. It has been successfully applied to detect and identify traces of chemical contaminants. So अगर trace में भी present है, then if Raman is signal is weak, तो फिर हमको तो नहीं मिलेगा. But क्योंकि we have now enhanced imaging sources like Raman resonance or SERS, we can detect and identify traces of chemical contaminants. Now, what kinds of things can be found out from Raman spectroscopy? Okay, first, the thing that can be found out is the frequency. Okay, frequency से हमको क्या क्या मिल जाएगा? नॉर्मल अगर सोचे तो अगर हमको कोई फ्रीक्वेंसी पता है तो हमको बॉन्ड लेंथ पता चल जाएगा, फोर्स कांस्टेंट. ठीक है, फोर्स कांस्टेंट पता चल जाता है, कितना स्ट्रेंथ बॉन्ड का है उतना पता चल जाता है, मासेस एंड पोजीशंस ऑफ एटम्स पता चल जाता है. ठीक है, सो वी कैन इजीली सी द लैटिस स्पेसिंग, हमको आइडिया हो जाएगा. ठीक है, वेव नंबर कितना है, उससे हमको स्ट्रेन ऑन द बॉन्ड कितना हो रहा है उसका एक आइडिया हो जाएगा. सो हियर, because we are using this kind of Raman spectra to find out the different kinds of lattice spacing and the bonds, here we can use Raman to find the fabrication processes of semiconductors. Okay. Also, acid devices, what kind of strains they can produce in some localized microscopic regions. We can see the micro domains, we can see the stress and strain in polycrystalline silicon structures and micromechanical systems using Raman. Okay, तो कोई भी surface phenomena जो है, we can find out using Raman spectra. So we can also see crystalline disorder. Okay, we can also see crystalline disorder, structural defects जैसे कि grain boundaries होते हैं nano crystals में, dislocation होते हैं. So any kind of dislocation in the crystal structure, any kind of defects in the crystal structure, any kind of damaged crystal structures we can see in case of Raman band. Okay, here is a example of SiG 0.3. So you can see it's an alloy and it has three main bands which relate to the silicon-silicon, silicon-germanium and the germanium vibrational modes. Okay. The next quantity that you can find out is Raman bandwidth. Okay, the next quantity is Raman bandwidth, and bandwidth is usually related to the lifetime of the phonons. Now, if you have a crystalline disorder, then the lifetime of the phonon will decrease and the bandwidth will increase. So if you have a broad bandwidth, okay, if you have a broad bandwidth, then you can say that there is some kind of disorder because the lifetime of the phonon decreased. Okay. So this is very useful when you're studying nanocrystalline materials. Okay, this is very useful in case of nanocrystalline materials, and you can study the defects or the size and stress in nanocrystalline materials. You can also study the films. Okay, the film layers also you can study, and you can make some assumptions depending on how broad the line width of the spectra is. Okay, you can see how broad the line width of the spectra is. Next is intensity. Okay, intensity is also it is related to the structure of the crystals. So if you have decrease in Raman spectra intensity, then some bonds are probably being broken. Okay, some bonds are being broken. So you can assume that some damage has occurred in the structure, okay, or some kind of a doping process has occurred, which is why there is a decrease in the intensity of the Raman modes. And this is also related to the breaking of bonds and change in atomic force displacement. So you can also correlate the Raman spectra intensity with micro inhomogeneities. So any kind of a displacement reaction within on the surface also, where some regions are more ordered or disordered than the other ones, then also you can use to find out that structure, surface level structure. So mainly in materials chemistry, Raman spectra would be required for different kinds of surfaces, and particularly for crystalline surfaces. What kind of structure it is, how it has been formed, what kind of inhomogeneities are there, what kind of defects are there, grain boundaries, what kind of boundaries are there, or any kind of superfluous structure on top of the normal structure are there or not, any kind of polymers are being formed or not, what kind of polymers are formed, how these polymers are oriented, how the crystalline structures are arranged. So all of that you can find out using different types and sensitivities of Raman spectrum. Okay, different types of spectrum. Even you can also find out the difference between diamond or graphite structures using the Raman spectra, because it is sensitive to short range disorder. So you can easily find out which one is the amorphous phase and which one is the crystal phase. You can easily find out which one is the amorphous phase and which one is the crystal phase. So in quartz also you can find out. Geologist chemistry also, they can find out from laser Raman microspectroscopy. So now many different kinds of Raman spectroscopy are coming up. In fact, some are coupling techniques like microthermometry with Raman microscopy to give more information. So in many mineralogical, geochemical, and geological processes also, you can find out the composition of minerals, whether any kind of fluids are there or not, any kind of gases are trapped in the minerals or not. That also you can find out, and then you can make some assumptions about the history or the origin of these materials. Also, because we're talking of minerals, many kinds of gems and jewels also, that also you can find out the impurities or the surfaces, and you can identify the gemstones, you can see the analysis of the nature, and you can also see how the jewels have been treated by which process. And we have already talked about how Raman spectra is used for process monitoring in industrial plants and quality control. So you can see that as well. So many different kinds of Raman spectra are also used for students of art and archaeology. So if you have any kind of manuscript or textile, even the mummies that are there, resin kind of artwork is there, ivory, wall painting. So Raman spectra can be used to date those artworks and also to establish forgery and frauds. Okay, so in a non-destructive kind of a way, you can find out whether the artwork is original or not. So they are used by archaeologists, art historians, and conservation scientists as well. Many kinds of pharmaceutical companies are also using Raman spectrometry to see the structural defects, how much the crystalline structure is there, whether any kind of hydrate formation is there, whether any kind of co-crystal formation is there or not. So here you can also use Raman spectra. Similarly, in the medical field also, Raman spectra has become a useful tool. So they can also generate information about the molecular composition, any kind of molecular interactions between the cell and tissue. So some kinds of Raman spectra, they can find out lipids, proteins, nucleic acids, and they have very specific fingerprints in the Raman area. So they are Raman active. And if you have cancer, sometimes you can see the transformation from the normal to the cancerous tissues, and they can, these variations, they can, you can you can detect these by Raman spectra, and they could be phenotypic markers of the disease. So now in coupling with other kinds of Raman spectra, particularly fiber optic Raman spectra, you can also replace biopsy for cancer studies, and you can use that in histopathology or immunochemistry. So this is a bird's eye view of Raman spectra, and we will also be discussing questions relating to Raman spectra today. So because we just have one last class tomorrow, so I'll prefer to revise and give some new information. So today we will finish off with all the questions from NMR, some problems of mass spectrometry, which is coming again and again in the exam. That kind of format we will discuss. And also, because we have just discussed Raman spectra, any questions relating to Raman spectra also we will discuss, and we will see how to solve these problems. Okay, so let us take a 15-minute break where you just revise everything. I will also be giving some PDFs now, and some I will be mailing, so you can share them in the group as well. So just go through some of the material that I'm sending right now, and you can just revise and come back in 15 minutes. Okay, so let us come back. We're going to discuss some questions now. So you can start writing. What is the principle of mass spectrometry? What is the principle of mass spectrometry? In what way is it different from other spectrometer methods? What is the principle of mass spectrometry? In what way is it different from other spectrometry methods? What is the principle of mass spectrometry? In what way is it different from other spectrometry methods? Next, write define chemical shift. Define chemical shift. Define chemical shift. List different factors affecting chemical shift of a proton in a molecule. List different factors affecting chemical shift of a proton in a molecule. Define chemical shift. List different factors affecting chemical shift of a proton in a molecule. Then write short notes. On write short notes on spin splitting. Write short notes on spin splitting and Merck-Lafferty rearrangement. Write short notes on spin splitting and Merck-Lafferty rearrangement. Spin splitting and Merck-Lafferty rearrangement. Next question. Mass spectrometer. Mass spectrometer employs mass spectrometer employs different types of ion sources. Mass spectrometer employs different types of ion sources. Explain the principle of explain the principle of chemical ionization method. Explain the principle of chemical ionization method used as explain the principle of chemical ionization method used as ion source in mass spectrometer. Explain the principle of chemical ionization method used as ion source in mass spectrometer. Next, you write the spectral details of an organic molecule. The spectral details of an organic molecule. Spectral details of an organic molecule having molecular formula C7H6O. Important spectral details of an organic molecule having molecular formula C7H6O are as follows. Are as follows. I'm putting the details in the chat box. I'm putting the details in the chat box. So in mass spectra, they are writing you have prominent peaks of M by Z is equal to 51, 77, that these are the base peaks, 105 and 106 as molecular ion. In IR, you have a medium intensity doublet around 2800 centimeter inverse, 1720 centimeter inverse, which will be strong, and 1600 centimeter inverse, signals below 750 centimeter inverse. And in NMR, you will have 7.3 ppm chemical shift, 5H multiplet, and 9.3 proton singlet. So just see this. What can be the answer? You will work it out. Okay, you will work it out. फर्स्ट मेथड होता है जब फॉर्मूला मिले उसका एक डबल बॉन्ड इक्विवेलेंट कर लेना चाहिए. ठीक है, डीबीई जिसको बोलते हैं रेफर टू योर स्टडी मटेरियल. ठीक है, स्टडी मटेरियल का जो यूनिट है जहाँ पे स्ट्रक्चर डिटर्मिनेशन इंटीग्रेटेड मेथड्स में है वो पोर्शन पढ़ना. उसमें डीबीई के मेथड्स फॉलो करे जाते हैं. सो व्हाट इज द डबल बॉन्ड इक्विवेलेंट? डबल बॉन्ड इक्विवेलेंट से एक इनिशियल आइडिया आ जाएगा. उसके बाद आईआर के सिग्नल से भी तुमको पता चल जाएगा कि क्या है. मॉलिक्यूलर आयन मतलब मॉलिक्यूलर वेट काफी क्लोज होगा, सो यू विल हैव एन आइडिया ऑफ द मॉलिक्यूलर वेट एज वेल. फिर डबलेट है 2800 मतलब you can think of aldehydes. 1720 will also be a significant indicator. CO stretching का भी आपको आ रहा है यहाँ पे indication. So you can find out the rest from the NMR spectra. So this is the kind of question that can come from integrated spectra structure determination. Next you write for Raman spectrum, one question is there. ये वाला कॉपी कर लो और 30 सेकेंड्स दे रही हूँ, कॉपी कर लो. Okay, right. Explain the origin of Stokes and anti-Stokes lines. Explain the origin of Stokes and anti-Stokes lines in a Raman spectrum. Explain the origin of Stokes and anti-Stokes lines in a Raman spectrum in terms of the quantum model of radiation. Explain the origin of Stokes and anti-Stokes lines in a Raman spectrum in terms of the quantum model of radiation. Next, what is the relationship between Stokes and anti-Stokes lines? What is the relationship between Stokes and anti-Stokes lines? ठीक है. नेक्स्ट लिखो explain the splitting of NMR signals. Explain the splitting of NMR signals due to spin-spin coupling. Explain the splitting of NMR signals due to spin-spin coupling by taking suitable examples. Explain the splitting of NMR signals due to spin-spin coupling by taking suitable examples. Next लिखो write notes on chemical shift. Write notes on chemical shift and write notes on chemical shift and Larmor precision. LARMOUR precision. The next question I am typing. Just give me time. 45. So, right, the important spectral details of an organic molecule having the formula C3H6O2. C3H6O2 is as follows. So in IR you have broadband 3000 centimeter inverse. In IR you have a broadband 3000 centimeter inverse and a strong band at 1700 centimeter inverse. Okay, I have put it in the chat box. Just see once. I'm also going to type the next details. Just copy this down. I've given the rest of the details of the NMR in the chat box. Please copy the problem down. Okay, so here again you will find out the DBE. I think it might be an alcohol here because of the broadband and also because of the 1H singlet. I might be wrong. Just work it out. Okay, just work it out from the mass spectrometry peaks and from the NMR, which is at a 12 ppm 1H singlet is there, and also from the IR that has a 3000 centimeter inverse broadband. I think it might be an intermolecularly bonded alcohol. So just confirm using DBE and then proceed. Okay, next, right? Next, right? State the characteristics of state the characteristics of tetramethylsilane. State the characteristics of tetramethylsilane, that is TMS, that make it a suitable choice. State the characteristics of tetramethylsilane that make it a suitable choice to act as reference in NMR. To act as reference in NMR. Okay, so state the characteristics of TMS that make it a suitable choice to act as reference in NMR. You know that the reference from where the chemical shift is measured, that is your tetramethylsilane. So you can write about that. Next is short notes on inlet devices in mass spectrometry. Short notes on inlet devices in mass spectrometry. Inlet devices in mass spectrometry and chemical ionization. Inlet devices in mass spectrometry and chemical ionization. Again, chemical shift has come in another question. Define chemical shift. What are the factors affecting chemical shift? That you can just put a tick mark again where you have previously written. Okay, explain the importance, right? Explain the importance of m plus 1 and m plus 2 peaks. Explain the importance of m plus 1 and m plus 2 peaks in mass spectrometry. Explain the importance of m plus 1 and m plus 2 peaks in mass spectrometry. Explain the importance of m plus 1 and m plus 2 peaks in mass spectrometry. Next, right, what are the conditions for Merck-Lafferty rearrangement? What are the conditions for Merck-Lafferty rearrangement? What are the conditions for Merck-Lafferty rearrangement? Explain with a suitable example. Explain with a suitable example. Then again, in another question, explain the basic principle of mass spectra. List different types of peaks obtained in mass spectra. So you have to explain it extensively. You've already got a question. Explain the basic principle of mass spectrometry. List different types of peaks obtained in mass spectra. You have to state it with examples. Next, this is an interesting question. Write it. Very easy, but you'll have to draw the spectra and write it. Okay, right. How will you distinguish? How will you distinguish? How will you distinguish How will you distinguish between ethanol? How will you distinguish between ethanol and dimethyl ether? How will you distinguish between ethanol and dimethyl ether on the basis of NMR spectra? How will you distinguish between ethanol and dimethyl ether on the basis of NMR spectra? Okay, ethanol and dimethyl ether on the basis of NMR spectra. So think about it a little. What will be the NMR spectra? What will be the NMR spectra? How many signals will be there? How many signals will be there? Two. Okay, there are two CH3 groups and they are equivalent. Okay, there are two CH3 groups and they are equivalent and they will show two signals. Okay, they will show two signals. So in dimethyl ether, that is CH3OCH3, you will get two signals. Okay, and they will not be split. They will not be split. But in ethanol, how many signals will you get? Calculate. In ethanol spectra, how many signals will you get? In ethanol, how many signals will you get? Three peaks, right? Three peaks. The CH3 group that will be there, okay, CH3, CH2OH, the CH3 group will be split into triplet. Okay, this will couple by CH2. So 2 plus 1, CH3 peak will be upfield and there will be a triplet. OH signal will also have one singlet peak. Okay, OH signal will not be split, so वो एक single peak होगा. And CH2 will have how many? CH2 will have how many peaks? Quartet. Okay, quartet. But here there is a twist. The CH2 peak, they can be split into a quartet by the methyl group, but there will also be some kind of influence from the OH proton also. So although usually from OH proton coupling is usually not observed, sometimes that kind of coupling is seen if you are taking a very pure sample. In case of usually ethanol, however pure you take it, some kind of impurities are present, so that ethanol does not usually occur. That ethanol coupling does not usually occur. It keeps on exchanging with the protons, so it does not show the coupling. So the most thing that you see is a quartet. In ethanol you see just a quartet. But if you're taking a very pure spectrum of ethanol and you're carrying out the procedure very carefully with a low temperature, then the OH can also couple and make it into 8 peaks. Okay, this is just for additional information. You can write or you can don't write, no problem. CH3 will be a triplet, high field. CH2 will be a little more downfield. Okay, it will be a quartet and OH will be a singlet. So you'll have 3 peaks in ethyl alcohol with splitting, but in dimethyl ether, you won't get any splitting. Next, right? Next, right? discuss the importance of discuss the importance of molecular formula. Discuss the importance of molecular formula and index of hydrogen deficiency or IHD. Discuss the importance of molecular formula and index of hydrogen deficiency or IHD in the structure elucidation of an organic compound. Discuss the importance of molecular formula and index of hydrogen deficiency or IHD in the structure elucidation of an organic compound. Next, calculate IHD. Calculate IHD in the following cases. Calculate IHD in the following cases. Calculate IHD in the following cases. I have given you three formulas. So you'll have to calculate IHD in the three cases: C10H22, C7H8, and C4H11N. Okay. Calculate IHD in C10H22, C7H8, C4H11N. Next, write what is meant by isotopic peaks in mass spectrum. What is meant by isotopic peaks in mass spectrum? What is their importance? What is meant by isotopic peaks in mass spectrum? What is their importance? Then again the questions have come regarding tetramethylsilane. Just put a tick mark where you have written about tetramethylsilane. Put a tick mark on spin-spin coupling, factors affecting chemical shift, and Mark-Lafferty rearrangement. Just put tick marks. These questions are repeated. Mark-Lafferty rearrangement, spin-spin coupling, factors affecting chemical shift. Principle of mass spectrometry and how it is different from other spectroscopic methods. Put a tick. Okay, now another question on Raman. Question, right? Draw a schematic energy level diagram. Draw a schematic energy level diagram. Draw a schematic energy level diagram showing the origin of Rayleigh line, showing the origin of Rayleigh line, Stokes line, and anti-Stokes line in Raman spectra. Draw a schematic energy diagram showing the origin of Rayleigh line, Stokes line, and anti-Stokes line in Raman spectra. Then next लिखो explain principle of resonance Raman spectroscopy and its advantage. Explain principle of resonance Raman spectroscopy and its advantage. Then write another question. The mass spectrum of butanoic acid, the mass spectrum of butanoic acid, the mass spectrum of butanoic acid with molecular weight 88 grams per mole, the mass spectra of butanoic acid with molecular weight 88 grams per mole gives a characteristic peak at m by z 60, gives a characteristic peak at m by z 60. Justify. ये देखना कौन सा क्लीवेज हुआ या रीअरेंजमेंट हुआ. Just find out. Mass spectrum of butanoic acid gives a characteristic peak at m by z is equal to 60. Justify. Now write down the formula, write down the formula for structural isomers, write down the formula for structural isomers of an organic compound, write down the formula for the structural isomers of an organic compound having molecular formula C3H6O, having molecular formula C3H6O. How can these be differentiated on the basis of NMR? So first you'll have to draw all the structural isomers, कौन से में branching है, and then you'll have to see कि NMR में क्या splitting हो सकता है, कितने peaks आएंगे और वो peaks कितने में splitting होगा. And isomers में because number of neighbors starts to differ, तो NMR में उनको differentiate करना आसान है. Structural isomers draw करोगे, उनका spectrum draw करोगे. Next लिखो. Write briefly about sample handling devices in Raman spectra. Write briefly about sample handling devices in Raman spectra. So अभी हमने डिस्कस किया कि ग्लास में सैंपल्स ले सकते हैं, प्लास्टिक में ले सकते हैं, क्वार्ट्ज में ले सकते हैं. So you can write about those and some more also from your study material you can see. Okay. Put another tick mark in chemical shift. Write its unit. ठीक है, chemical shift का unit अच्छे से देखना है. और spin splitting में tick mark मारो. Mark-Lafferty rearrangement and example में tick mark मारो. अगेन केमिकल आयनाइजेशन जहां पे लिखा था वहां पे टिक मार्क करो. ब्यूटेनोइक एसिड वाला जो जस्टिफिकेशन था उसमें एक टिक मार्क मारो, दैट इज ऑल्सो रिपीटेड. टेट्रामिथाइल सिलेन जहां पे यूज किया था वहां पे जहां पे लिखा है वहां पे एक टिक मार्क मारो, दैट इज रिपीटेड. Okay, now you write explain the following terms. Explain the following terms. Explain the following terms. Nitrogen rule. Explain the following terms. Nitrogen rule, then metastable ions, then metastable ions, and then index of hydrogen deficiency. Nitrogen rule, metastable ions, index of hydrogen deficiency. Then write state any two quantitative applications of mass spectrometry. State any two quantitative applications of mass spectrometry. State any two quantitative applications of mass spectrometry. Next, write explain why it is advantageous to use a magnet, why it is advantageous to use a magnet with higher field strength in NMR spectroscopy. Why is it advantageous to use a magnet with higher field strength in NMR spectroscopy? Then write how many signals do you expect in the NMR spectra? How many signals do you expect in the NMR spectra of 2 bromopropane and 1 bromopropane? How many signals do you expect in the NMR spectra of 2 bromopropane and 1 bromopropane? ओके. अच्छा, जहां पे केमिकल शिफ्ट और टेट्रामिथाइल सिलेन था वहां पे और एक बार टिक मार्क मार दो. दोज हैव कम इन जस्टिफिकेशन. ठीक है, जस्टिफाई why TMS is used as an internal standard. Justify why magnitude of chemical shift is proportional to strength of induced magnetic field. ये वाला देखना है, magnitude of chemical shift is proportional to strength of induced magnetic field. Then justify why Raman shift positions of Stokes and anti-Stokes lines are equal but opposite. Then why can protic solvents not be used to record the PMR spectrum of an organic compound? Why can protic solvents not be used to record the PMR spectrum of an organic compound? Then next, write draw a labeled schematic diagram of an NMR spectrometer. Draw a labeled schematic diagram of an NMR spectrometer showing various components. Draw a labeled schematic diagram of an NMR spectrometer showing various components. Again, characteristics of mass spectra, principle of mass spectra, then spectral lines due to chemical shift, वो सब फिर से आ रहा है. Chemical shift के factors फिर से repeat हो रहे हैं. Then calculation of IHD for different types of compounds. ठीक है, different kinds of compounds benzene के लिए दे दिया है, तो उसका भी IHD find out करना है. तो different types of IHD को practice करके जाना है. Just seeing if there is any different kind of question that we haven't done yet. हाँ ये वाला लिखो, ड्रॉ पास्कल्स ट्रायंगल. ड्रॉ पास्कल्स ट्रायंगल. Draw Pascal's triangle. How is it useful? How is it useful in predicting relative intensities? Draw Pascal's triangle. How is it useful in predicting relative intensities of split lines? How is it useful in predicting relative intensities of split lines? Write the possible spin orientations. Write the possible spin orientations due to three protons of the methyl group. Write the possible spin orientations due to three protons of the methyl group. ठीक है. Next लिखो, explain the variation in the position of explain the variation in the position of the OH signal. Explain the variation in the position of the OH signal in the NMR spectrum of phenol. Explain the variation in the position of the OH signal in the NMR spectrum of phenol as a function of concentration. As a function of concentration. ठीक है. Next, write explain diamagnetic anisotropy. Explain diamagnetic anisotropy with the help of a suitable example. Acetylene का example दे सकते हो. Explain diamagnetic anisotropy with the help of a suitable example. केमिकल शिफ्ट और उसका इलेक्ट्रॉनिक सर्कुलेटिंग इलेक्ट्रॉन करंट्स कैसे हैम्पर करता है शिफ्टिंग को, हाउ इट अफेक्ट्स. यू कैन राइट explain diamagnetic anisotropy with the help of a suitable example. You can take the examples of benzene and acetylene. Pascal's triangle again repeated. What is Pascal's triangle? Significance in NMR spectroscopy. थोड़ा घुमा दिया. ठीक है. Pascal's triangle, significance in NMR spectroscopy. नेक्स्ट लिखा है एक्सप्लेन द फ्रैगमेंटेशन पैटर्न. एक्सप्लेन द फ्रैगमेंटेशन पैटर्न ऑफ मिथाइल अल्कोहल. एक्सप्लेन द फ्रैगमेंटेशन पैटर्न ऑफ मिथाइल अल्कोहल and draw the mass spectrum. Explain the fragmentation pattern of methyl alcohol and draw its mass spectrum. Describe resonance Raman spectroscopy. This had come earlier. Resonance Raman spectroscopy. Describe resonance Raman spectroscopy. Tetramethylsilane again repeated. Then Mark-Lafferty rearrangement repeated. It is here the question is slightly different. What is Mark-Lafferty rearrangement? Explain with example of butanal. Butanal. Explain with the example of butanal and predict its mass spectral features. Explain with the example of butanal and predict its mass spectral features. So again, Pascal's triangle is repeated. Then tetramethylsilane repeated. Then you can write explain the origin of isotopic peaks. Explain the origin of isotopic peaks by considering example of explain the origin of isotopic peaks by considering the example of CH3Br. By considering the example of CH3Br. Next is a question that we just discussed. Explain the NMR spectrum. Explain the NMR spectrum of ethanol. Explain the NMR spectrum of ethanol in low resolution and high resolution conditions. Explain the NMR spectrum of ethanol in low resolution and high resolution conditions. So low resolution में तुम्हारा जो CH2 ग्रुप होगा उसका क्वार्टेट आएगा. High resolution conditions में वो octet हो जाएगा because the four peaks will again be split into two because of the influence of OH. And वो depend करता है resolving power में and what conditions you are using to predict the spectra. अगर रफ ले रहे हो तो क्वार्टेट आएगा, अगर एकदम सेंसिटिव इंस्ट्रूमेंट में कर रहे हो रिजॉल्विंग पावर जिसका हायर है तो उसमें ऑक्टेट आ जाएगा. अ क्वार्टेट स्प्लिट इनटू टू ईच. हाउ एंड व्हाई इज इट डिफरेंट? आल्सो प्रेडिक्ट द मास स्पेक्ट्रल फीचर ऑफ द मॉलिक्यूल. तो एनएमआर और मास का कंबाइन करके भी दे रहे हैं. आल्सो प्रेडिक्ट द मास स्पेक्ट्रल फीचर ऑफ द मॉलिक्यूल. Explain the terms base peak, molecular ion peak, and fragmentation. Explain the terms base peak, molecular ion peak, and fragmentation. So again, Mach-Lafferty rearrangement has been asked to be explained, but last time it was butanol. Okay, here the example is 2-pentanone. You can write that 2-pentanone. 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 Explain Mach-Lafferty rearrangement with 2-pentanone. Then anisotropy of a chemical bond क्या होता है? Explain with example. Benzene and acetylene you can again explain. Next, right? What is the requirement? What is the requirement for a nucleus to show NMR spectrum? What is the requirement for a nucleus to show NMR spectrum? Which of the following nuclei? Which of the following nuclei will show NMR? Which of the following nuclei will show NMR? 16O, 13C, 16O, 13C, 24 mg, 19F, 31P, 32S. 16O, 13C, 24 mg, 19F, 31P, 32S. ठीक है, इसमें इवन मास नंबर वालों को इक्वल नंबर ऑफ प्रोटॉन्स एंड इलेक्ट्रॉन्स अगर होगा तो नहीं होगा. So 13C, 19F and 31P will show NMR. 13C, 19F, 31P will show NMR. So example of ethanol और methanol लेके mass spectrum बार बार समझाने को बोल रहे हैं. So you can do this. IHDB again benzene C4H4 इसके लिए आता है. Pascal triangle also is coming again and again. Also ethanol का NMR spectra in low resolution, high resolution, popular question. Then next, isotopic peaks in mass spectra कैसे होगा वो भी that has been done. Sample handling, internal standard कौन सा है. Then benzyl alcohol का NMR spectrum. Okay, benzyl alcohol का NMR spectrum. So you can write the features of benzyl alcohol's NMR spectrum. Okay, Raman का एक है. Explain the particle theory of Raman effect. Explain the particle theory of Raman effect. Explain the particle theory of Raman effect with the help of schematic representation. With the help of schematic representation of the energy changes. Explain the particle theory of Raman effect with the help of schematic representation of the energy changes associated with associated with associated with excitation, Rayleigh scattering, with the help of schematic representation of energy changes associated with excitation, Rayleigh scattering, and Raman scattering. Then write important spectral signals predict the important spectral signals expected in IR and NMR. Predict the important spectral signals expected in IR and NMR of ethyl ethanoate, or benzoic acid. Ethyl ethanoate or benzoic acid. ठीक है. So NMR, mass or Raman spectra mostly we have covered, and if time permits we'll solve some more problems for mass spectra. ठीक है. Mass spectra का some problems have just left out because they're of the similar nature, integrated वाले. So if time permits we'll again do those questions tomorrow. So we have covered Raman spectra today. We've given you some materials, and we have covered the questions of Raman, Raman, NMR, and mass spectra. Some questions are repeated, some questions are repeated with a twist. So you'll have to go through the study material and solve for them, क्योंकि in type of topics में application oriented बहुत आता है. So problems solve करना पड़ेगा, spectrum draw करना पड़ेगा, IHD calculate करना पड़ेगा, prediction करनी पड़ेगी. So please practice as much as you can. Okay. So thank you so much. We'll be wrapping up today's session. Tomorrow is the last class. So I hope we've had a pleasant journey till now. Okay. So thank you so much.
Thank you, madam. Good night.
Good night.